Now it's on YouTube. I'm just well, it's still not 1:30.
Oh wow! So is this YouTube the channel for
UFRGS, URGS.
UFRGS RGS YouTube? I'm gonna send it to my mom.
Oh,
Yeah.
then you're not the only. Then your sister's not the only superstar in the family.
No. Is this one a UFRGS TV?
It's the link that's together with the Zoom.
Oh, okay. Let me see if
I
I can.
sent you on Monday a Zoom link and then a YouTube link.
Oh, but not to the WhatsApp, right? It's not. It's on the email.
I think both. I think email. Yes, email.
Email, yeah. Yeah. Well, anyways, I'll send them the link later, and then they can
I can find it here just a second.
Yeah, that's fine. If it goes well. So yeah, as I said, I don't know how to make the main screen in my laptop, so I have to be looking a bit onto the right, but I hope that's okay for everyone, yeah.
The YouTube link is in your WhatsApp, Maria.
Oh, thank you.
Já tá pronto? Já tá transmitindo ainda não? Boa tarde, pessoal. Então, esse é o segundo seminário do semestre. A gente tem uma lista de presença que vai passar no final. Você tem uns alunos da graduação que vai fazer parte conta de uma disciplina, né? Então, aí vocês podem assinar. Também, vocês são convidados a fazer perguntas no final do seminário. E se vocês tiverem vergonha, vocês podem escanear aqui e fazer a pergunta no Google Doc, tá bom? Então, a gente vai passar para vocês escanearem. So welcome everyone to today's seminar. Today we have Maria de Juan Ovelar, who is a postdoctoral researcher at the University of Warwick in the UK. So Maria is an aerospace and materials engineer by training. She got her PhD in astrophysics in Leiden in the Netherlands in 2013. After spending some years working for Airbus in Spain and the Instituto Nacional de Técnicas Aeroespaciales and the European Space Agency. Her thesis was at first focused on instrumentation, specifically on imaging polarimeters, but it then developed into research related to protoplanetary disks, observations, and observational diagnosis, which she worked on for a few years after a postdoc at the Liverpool John Moores University in the UK. After 2 long maternity breaks and some postdoctoral contracts in different fields, she returned to the field of planet formation in protoplanetary disks in September 2023 as a postdoc at the University of Warwick. Maria, it's very nice to have you here. Thank you so much for accepting our invitation. You may start when you're ready.
Oh, thank you very much, everyone. Let me know if you can't hear me or if there are any problems. Of course, you can stop me. So thanks for the introduction, Anna. Yeah, I'm Maria de Juan Ovelar, and I'm really thankful to you all for giving me this opportunity to tell you about my research interest, which deals essentially with multi-wavelength observations and what I call diagnostics, specifically applied to protoplanetary disks. So, there we go. Yeah, sorry. So protoplanetary disks are a stage, natural outcome essentially of planet formation, of star formation, sorry, where we have this cloud of dust and gas that's collapsing and it's forming a star. The star is born and starts radiating. And then as it pushes material outwards, but the material still infalling into the star, the angular momentum of the star that's just formed then flattens out this excess dust and gas into a disk essentially. And they are accretion disks. So these disks are rotating around the star, but they're also infalling, still feeding material into the newborn star. So they really are a natural outcome of star formation. And we do know a lot about these disks. We have observed many of them so far. And we have images, we have spectra, sorry, and then we have tons of data now. And the next stage in the process, as we can see here, is the formation of planets. So at some point, after about 10 mega years, all of this surrounding material in the form of a disk is dissipated. And we think fed into smaller bodies that grow to be planets or brown dwarfs or companions to the star. So that's the thing we know, again, that we have tons of exoplanets that have been found to date. I'll tell you a bit more in detail about that. But essentially what I'm curious about is, and what is an open question still, to this day, despite the wealth of data that we have, is the question of how do we go from one phase into the other phase? And that's essentially what I focus my research on. That's the mystery I want to solve. So starting with exoplanets, as I said, we have tons of data on exoplanets, thanks to missions like Kepler and TESS. To date, I searched online, and on 26th of March this year, we had 5,800, more than 5,000 exoplanets detected and confirmed with, and I want to draw your attention to this number. I didn't know this when I searched. TESS still has 7,500 candidates for planets that are waiting to be confirmed. So this could be something like 12,000. It's incredible. It's incredible the amount of data we have on detection of exoplanets. And these planets are also, we know, arranged in exoplanetary systems. And we have more than 4,000 exoplanetary systems. So these planets that we have found are arranged in systems that actually resemble very little our solar system. And we have data of these planets like mass. We have sizes of these planets that are estimated, and we use those to make estimates of the density of the planet and also the composition. For some of these planets, we have some spectra taking, and then we can tell a lot about what's inside the planet, in the atmosphere of the planet. And thanks to the density with the mass and the size, then we can, make guesses about the composition of these planets. And that has left us with, this is obviously an artist impression, but it is based on data, on real data. What it's called the exoplanet zoo, which is like an immense amount, this is only a subset, obviously, of properties for these planets that are very different from the planets we know in our solar system. Some of them are similar masses, obviously. Some of them are rocky, some of them are gaseous. But essentially, what we figure out so far is that we are quite different from what we can see, which is obviously biased, but by the limitations of the instruments. But in any case, we have this beautiful richness and variety in the zoo of exoplanets, and we have to find a way of creating these planets with these very different properties and compositions. And that all has to come from a place in the star-forming cycle, and we think happens in protoplanetary disks. So these protoplanetary disks, or disks that are thought to be hosting planet formation, have been also observed, and we have tons of data. This is a little collage with a lot of images from different instruments, just to give you an idea of the richness also and variety of the morphologies and the substructures that we have detected in these disks to date. So again, how do we go from the richness and variety of morphologies in the distribution of dust and gas around newborn stars into the exoplanets and the variety of compositions and arrangements for planetary systems that we see? That is what I want to address with my research, and that's what I've always had my focus on. So it all happens here in disks, and that's where I'm going to start my story. Again, these disks are composed of gas and dust. That's remnant from the cloud where the star forms. And they are rotating around the star, but they're also infalling. So these are essentially accretion disks as well. So the gas is still feeding the newborn star. The star keeps on growing. It's a very turbulent and very dramatic, I like to say, sight. And these disks, as I said before, I mentioned, live for around 10 million years. And after that, we know that the frequency of stars around disks around young stars decreases very rapidly. So we have those 10 mega years to sort of form planets around the stars that we then end up detecting with these missions like Kepler and TESS. So just to give you an idea of how complex these sites are, this is a really nice sketch that's taken from a very nice review that I recommend everyone interested to read, which is the Bai et al. Review on the protostars and planets, PP7, that was published in 2023. And it gives an idea of the processes we think are going on, and the range of physics is just mind-blowing. I'm not going to explain in detail all of the different mechanisms that we see here. By the way, can you see my pointer? Can everyone? You can see the pointer? Yeah, okay. So, but if we just keep ourselves to the outside of the disk and not go into the details of each one of the processes that we're considering that goes as an input to the planet formation, we can sort of get a feel for how complex and dramatic and turbulent indeed these sites are. So starting from here from the left, we have gravitational instability and hydrodynamical processes. Those affect mainly the gas, but then the dust is believed to follow the gas largely. And then these processes affect mainly the dynamics of the gas and dust in the disk, which essentially drives where the material goes and is located in these disks. Then we move on to have tidal processes, which are to do with gravity and gravitational interactions that can come from inwards inside the disk and also outwards. Because we have to remember the star formation process most likely doesn't happen in isolation. Most stars do not form alone. And these stars are in this planet, in these star forming regions that are with high levels of radiation, high levels of high mass stars, and surrounded by stars that are relatively dense in terms of number of stars. So all of these can fly by and affect the evolution of our disk, but we also have dust coagulating, gas accreting into planets forming spirals, moving around the dust and the gas, causing substructures in the disk. And that affects, again, the gas and the dust and the evolution necessarily of the disk. Then we move on to consider dust processes. So we have both chemical and physical processes. So we have dust that's crossing ice lines as it flows from the outer regions in the accretion disk toward the inner regions of the disk. And as it heats up, because it's moving from colder to hotter, all of the ice little layers, top layers that are frozen, then those might sublimate, and then the composition of the dust grain changes, that those sublimated molecules, then are fed into the gas for the disk. So all of this affects the evolution of the disk eventually. And we also have processes that happen in the dust that are physical. So like we have dust grains that come together to form a larger grain. This is coagulation. We have dust grains that are largish that smash each other, and then there's fragments. So we have all sorts of things going on as, for example, instabilities, like very large. This particular one is called streaming instability, which is believed now to take place in places, locations where there's a lot of large dust grains. Then these dust grains very rapidly start growing and forming, hopefully, planetesimals that then start feeding gas in and eating out the material around them. So all of that is going on. And finally, but not least, never least, the magnetic fields. So magneto-hydrodynamical processes are there. So this star is a star that's just born. Magnetic fields are all over the place at the time. It's a very unstable situation in terms of magnetic fields, and that all fits into the turbulence that affects the gas and then the dust in the disk. Now, on top of that, we have high radiation photoevaporation from the star. So the range of physics that we have to deal with when we think about the conditions under which planet formation takes place is simply massive. And this also happens on massive spatial scales, because these disks are very large. Some of them are about 500 AUs. It's not the norm, but it is in the hundreds. So just this only should give us an idea of why then we end up having systems that are so different and so varying, and planets that are so different from the ones we know in the solar system. So moving on, I want to show this sketch, because the only way we can actually say something about the mechanisms taking place in these disks is actually trying to follow the material. So the only way we can observationally confirm that one mechanism or another is taking place at a certain location in the disk is to be able to trace the different species of material within the disk. And in order to do that, it's interesting to know how this material shows up when we observe. And that's why I believe this sketch is really useful, because it's very simple. It's not complete by any means, but it is very clear in showing what the different components of these different species in the disk show up as when we observe, and also gives an idea at the top of the observational techniques that we can use to detect these components. So essentially we have, if we start from the star, we have the star accreting, and that shows up in the UV continuum radiation and also H alpha and recombination lines. Then we have a component of very hot gas, because the dust is removed from the nearby regions of the star by the radiation. So there's just gas in here, but it's really hot gas. So that shows up in the near infrared continuum, as well as atomic lines and molecular lines that we can trace with different instruments. Then we have a component of very hot dust that's directly illuminated by the star. And this dust shows up again in the near infrared dust continuum wavelengths, which is very near the visible, but then not as close as that. And then we have growing in size for the dust grains, and also in decreasing in temperature, what is called the planet-forming region, which is like the mid-size region in radial distance. And then this one is emitting in longer and longer wavelengths into the infrared. So we have the mid-infrared dust continuum, also some molecular lines coming from here. And then finally, we have the cold dust, large grains of cold dust that show up only in the submillimeter at longer wavelengths because it is much less temperature for that dust. Now, in this sketch, there are some things missing. There's an important component that's missing from this one that is called the midplane. The midplane would be this area, this region in the center of the disk, where the large grains of dust that are floating around in the gas up here and below, then they settle into that midplane and they are shaded from the radiation. So then they don't get to heat up that much, and it's a very cold component of the disk. It doesn't show up in the sketch, but is an important component. I'll show you later why. And there is also another component that is not here, which is the small dust grains that are in the surface layers of the disk that actually reflect and scatter the radiation coming from the star. And these are small micron-sized grains that we can detect if we look with polarimetry, which was what my PhD was dedicated to. Because with polarimetry, because this is horizontally polarized, and then if you look in polarize, if you do polarimetry of these sources, then you can trace the morphology. You don't get any information about the bulk of these dust grains, but you can trace the morphology of the surface of the disk by following those small grains in the surface. So we have also a very large range of wavelengths that we can utilize to sort of characterize these very complex and interesting sites. And in the top here, we get to have an idea. Again, it's not complete, but of the observational methods that we can use. So we can use near infrared interferometry to work with the gas, the hot gas and the hot dust, mid-infrared interferometry for all of this area. And then at the time, there was only, because this is 2010, so it's a very simple and again, not complete sketch, but I like it because it gives a really clear idea of the observational side of it. So at the time, it was only direct imaging was only provided by Hubble, and it was only available to trace these colder regions of the disk. And then ALMA was at the time planned to come online, and ALMA is working on the submillimetre and millimeter wavelengths, and that traces again the large grains that are colder in the midplane and also in this outer disk component. So this is clear. What people did historically to study protoplanetary disks was to look into the SEDs. So SEDs, the spectral energy distributions, for those who may not know about this, are essentially plots that show the energy, the flux coming from a source, from a star, against the wavelength. So in the x-axis you have the wavelength, and in here whatever measure for the flux you want, or the energy. So if you measure the flux and the amount, the intensity of light you get from the star at different wavelengths, then you end up with a profile. That's the outside line here. This is if you look at a star that has a disk, because a star only would have what we call like a black body type emission profile, which would be this yellow one here. This is called here the stellar contribution, and all the rest is called the infrared excess. And this is how at first it was inferred that there must exist some material surrounding the stars when there were no images of these disks. And it was known because there was this excess of infrared emission, and that is why it's called the infrared excess. Now, if we go back to our scheme, our little sketch here, then we can identify actually by the temperature that we estimate these components to be. We can identify the different contributions that they have to the SED. So in red here, we have the inner dust, inner disk or inner rim contribution. Then in blue, we show here the outer mass reservoir of dust in the disk. And then it doesn't show here, but it should be in the sketch. The disk midplane is the coldest contribution to the SED. And what was very early noticed is that a lot of these disks that had infrared excess in the SED also had a dip. So aside from the contribution of the midplane, there is a region here that is missing, and that is why it was labeled the planet-forming region, because a lot of these disks were missing it, and it was assumed that material was missing from the disk, and the immediate idea is that this material is being transmitted into the planets as they form, or eaten by the planets, as I like to say. So indeed, when this happened, there was a lot of studies that show that the expected emission for a full disk was like this, and we actually have sources that show an SED that's continuously profiling in this way. But then when you have one component missing, which in this case would be this yellow one here, then you get a dip into the infrared excess, and that was associated with a gap of material in the disk. And there goes Hubble, which at the time was the only thing that people had, to sort of confirm that indeed there seems to be a gap in the material in some of these sources that presented an SED with a dip in the infrared excess. But move on a couple of years, and then in 2015, in comes ALMA, the wonderful ALMA that we all know and love, showing a mind-blowing high-resolution protoplanetary disk that we could never imagine was going to be as good as it was. So in here we can see how it is indeed the case that we have missing material. We have these narrow rings, several rings, highly symmetric substructure here. We have a more extended ring here with a larger gap here, then a series of narrow rings. And this was like, everyone was like, what is going on? This is amazing. We could never in a million years imagine we were going to be looking at something like this. So this was, I mean, it started a revolution really in the field, because for the first time we could actually take images of what we thought was planet formation taking place, like happening, the consequences in the morphology and of the dust and gas in these disks that planet formation has. Now, a couple of years after that, sorry, what?
Size of the picture, the physical size of the picture.
So Horacio is asking the physical size of the ALMA photo. Yeah. In parsecs, astronomical.
Oh, I don't know, to be fair. I don't know the number by heart. I could search for it, but I'm sorry, I don't know. I could say a number, but I'm not gonna know it. Sorry. I don't know these things by heart. But yeah, but I've got other images that show the actual scales, so we can go on. I'm not sure exactly how far HL Tower is, and that could give an idea of the spatial scale, but maybe with other plots we can answer that question. But I say so. Yeah, I'm not going to say anything because it's going to be wrong. So. Okay, so a couple of years later, then another instrument in the Very Large Telescope in Chile as well was introduced, and this is the wonderful Sphere. Sphere is an imaging polarimeter, and that's me, by the way. I always find an opportunity to show this photo because it was one of the coolest things that I did, because I went there to observe. But yeah, Sphere is amazing. It is a near infrared polarimeter that traces, as I say, the small dust grains on the surface of the disk, and it provides extremely high resolution images like this one of TW Hydra, which was the same source that I showed you was observed with Hubble to confirm these gaps in the material. And indeed, we can see that there are gaps in the material. So in here, we have this large gap that was already detected by Hubble, but then the resolution is astonishing, and also the capacity of the instrument to go to the inner regions of the disk, where there is yet another gap here. And this is, again, part of the revolution that we've undergone in the past 10 years with observations of this kind, because it is quite insane what we're looking at these days. And this was back in 2015, 2017. But then ever since, we've gone and looked into a large number of these disks, and we have now surveys done with both ALMA and SPHERE of a ton of these protoplanetary disks. And just to remind you, because this is going to be key for what follows in the story. So we have images with ALMA in the submillimetre and millimetre wavelengths, and these trace large coldish 1 millimetre dust grains. So what I'm going to call from now on large grains are about 1 millimetre in size. So all of these different morphologies and substructures you see here pertain to the component of the large cold dust grains in the disk. And then we also have amazing and very high resolution images of a large number of disks with SPHERE, which again looks in the near infrared polarimetry, which traces small 1 micron dust grains on the surface of these disks, the surface layers. And this in particular is a survey done by Garuffi et al. In 2023, published in 2023, where they went on to look into the Taurus star-forming region here. This is Taurus in the background, and then each one of these stars here is a target of the survey, which you can get the images around here. And just the scale of what we can do now and the detail of what we can resolve now is just, it just doesn't cease to amaze me. Every time I look at it, I just think this is one of the most beautiful things that I've seen in my professional time. But what I still think is missing is that we have these amazing ALMA images and amazing SPHERE images, and we have demographics linked to star-forming region conditions. But we're mostly still operating on a single wavelength basis for systematic surveys like this, right? Occasionally, when you have a particular source that you're interested on, then you can go and retrieve images taken with different instruments and sort of try and piece the thing together. And I'm going to show a couple of examples of this, but in general, it's not a systematic practice when one undergoes these surveys. So what I will argue for is that multi-wavelength observations are needed to be used systematically in the case of diagnosing what is going on in the disk. And to show a couple of examples of this, this is Fomalhaut. This is not a protoplanetary disk. This is an old star, 440 million years. So this disk will actually pertain to the debris disk category. So it's not a young disk forming planets anymore. We assume that the planets have already been formed in the system, and what is remnant here is a ring that would be akin to the Kuiper belt and something like that. So in this case, because this is a very famous disk, we have images with very different instruments. So we have Hubble images looking in 0.6 microns. Then we have near and mid infrared images with James Webb. We have Sophia at longer infrared wavelengths, and then yet longer infrared at 70 microns with Herschel. And then finally, the images with ALMA tracing indeed a ring of dust grain that's cold in the disk. And the striking thing here is that if we piece all of these images together, then we can get a lot of information about the evolution of the material in this disk. And this is indeed what's been done in the literature. Another example that's very striking is the case of PDS 70. This is a protoplanetary disk. This is a very young system where pieces of information retrieved with ALMA, sphere, and MUSE have been put together, to show us planet formation actually taking place. So at first there were observations taken with sphere. These are not the first observations of this disk by any means, but these are the first ones relevant to this puzzle, where these blobs were detected. And these blobs, when then the people studying this then went on to look into H alpha with an instrument called MUSE. Again, H alpha is tracing accretion processes to try and confirm if these were planets that were accreting or not, or they were just simple clouds in the disk that were formed. And indeed, they show up in the H alpha images, confirming that there is an accretion process happening at that location. And then the final piece of the puzzle was ALMA, which I'll tell you a bit more detail about this later, but shows a ring of dust, coal dust, that is trapped by the pressure maxima that appears in the gas when you have planets in the disk. I'll show you about that in a minute. But the important thing here is that we can learn a lot about the planet formation related features and mechanisms by piecing all of these puzzles together. So in my view, it is essential and it is key to consider multi-wavelength observations to get the coherent picture of what is happening, because none of those images by themselves could have tell you the whole story of what is happening in this particular source. So again, this is done for sources, particular sources, but the goal would be to have a much more systematic way of diagnosing planet formation mechanisms in the disk. And this is what I call the multi-wavelength diagnostics for protoplanetary disks, which is this idea that we might start from observations, which is what we've seen so far. So we find observations that maybe don't match, and we try to build synthetic observations based on models that try to mimic these systems. And then we link that to theories of planet formation one way or another. But it can also be done in a different direction. We can also start with a mechanism of planet formation that we think in theory could be taking place. We can then build the synthetic observations, how the different materials in the disk will show up at different wavelengths, like we see here. And then we could link that to observations. And in order to support the case, I'm going to show you two case studies that I've been involved in that have dealt with the two directions of these multi-wavelength diagnostics system that I like to look into. So the first case is called missing cavities. This is back in the days of my PhD, 2012. It was called a missing cavities problem in the SEEDS survey. So the SEEDS survey was a survey that was done by Dong et al. Published in 2012, where they targeted disks with a polarimeter that had been known to hold a gap, to have a gap in the continuum emission of longer wavelengths. So let me show you here. So observations at submillimetre emission, again, tracing large dust grains, were showing cavities in different targets of a certain survey done, not with ALMA, but different instrument. And then they went with the polarimeter to trace the small grains, and then they realized there are no cavities in these images. Now, what you see here in black is not a cavity, is what is the coronagraph of the instrument. Because at near infrared wavelengths, we need to block out the star as we look into the disk, because otherwise the intensity of the star is too high, we wouldn't be able to see anything around it. So we have to use these coronagraphs, and that's unfortunate because we lose a lot of information of the inner regions of these disks. But as far as the coronagraph would allow us to see, there were no cavities compared in size with the cavities that we're seeing in the submillimeter emission at 850 microns. So large grains, there is a cavity. Small grains, there is no cavity. And at that same year, there had been a paper published by Paola Pinilla and collaborators in 2012, where she presented this idea of dust traps. And I'm going to explain, I hope, in simple terms what this is about. So they suggested that if you have a planet embedded in the fluid, that is the gas and the dust in the protoplanetary disk, this planet causes a wave, so to say, and a pressure maximum at the peak of this pressure wave, that would increase the density of the gas in that area, will carve a gap depending on the mass of the planet, and will leave you with a peak in density at a certain radial location exterior to the planet. So we can see here, this is the gas, the map, the 2D maps of gas of a disk of same mass, but then with different mass for the planets embedded. This is the 1 Jupiter mass planet. This is the 9 Jupiter mass, 15 Jupiter mass. And as we can see, the gap is getting wider and wider as we move out. If we look into the dust, and this is a bit of a complex plot, but I'll try to explain. Imagine that this white line here is not exactly that, but it acts as the profile of the density in the gas, right? So the planet is located here, and we have our gas density, and then we have a gap, a depth in this profile, and then we have a peak here that increases as the mass of the planet increase. Now, what we see in the column bar here is the density of dust. So the yellower, the higher the density. And what we see in the y-axis, this is for the radial location in the disk, is the size of dust grains. So the way to read these plots is that depending on the mass of the planet, we always get a piling up of dust that follows that pressure maximum in the gas, and it's trapped there. But this high density is it's composed of dust grains that are large in size. So this is in centimeters. But what happens is that depending on the mass, the smaller dust grains, which are these ones here, are able to flow through the gap because the gas is still flowing, and then populate the inner regions of the disk. So an easier way to look at this is if we do the profiles for all of them, right? So this is part of my study that I published in collaboration with Paola Pinilla and the people that have run those simulations. And this is a distribution of dust grains that we put into the disk. This is the gas showing up here in the dotted black line for a 1 Jupiter mass planet, for a 9 Jupiter mass planet, and for a 15 Jupiter mass planet. And then we have the dust bin in dust grain sizes. So we have 4 sizes going from blue. These are micron to 10 micron dust grains. And then we end up at 1 centimeter. So these are the largest grains. Green and orange are like medium size. So as we see here, the profiles of the especially long grains, the large grains and the small grains are strikingly different. And this is interesting because when you look with long wavelengths in the submillimetre or near infrared polarimetry, you're going to be tracing the blue and the red lines. So this is what we did. We built the synthetic observations for these cases, hypothetical disks. These were not trying to simulate these particular targets that have been observed, but it was useful in confirming the idea that these dust traps, what they do is that these dust traps pile up large dust grains while allowing the small grains to flow in, which ends up showing up as no gaps at the position of the planet for the near infrared images, where there is a much larger cavity in the 850 micron emission. So again, this way of using synthetic observations to connect the theory with the observations was very useful in 2 ways. Firstly, because it showed that we can explain this kind of discrepancies in different wavelength observations of the disk, because we're tracing essentially different components of the material in the disk. And also because by doing this exercise with an ideal disk and different planet masses, we could build a function for an estimate of the mass of the planet that's causing this signature. If you give me the position of the edge of the cavity in this image, and the position of the ring in this image. Then if I have the ratio of those two locations, then I can tell you how large is in mass is the planet that's causing this signature. And very quickly, I'm going to tell you about the second project that I'm working on that's doing the same, but in the other direction. So in theory, we start in this case, we start with theory, and then we build the synthetic observations, and then we try to connect that with observations that have already made. So it's not targeted for that particular case. But this is a theory of planet formation that's called sandwich planet formation. And it was essentially devised as a mechanism of forming planets that are small in mass in between two large planets. So what you see here is different planetary, exoplanetary system. This is real data. And we have the masses for these planets and also the location. You have here the orbital period of the planets. The color, the redder the planet, the higher the mass, and the bigger the planet, the higher the mass as well. The gray planets are planets we don't care about because they're not the sandwiching ones. And the blue ones are the ones that are smaller mass in between two larger planets. So there's a bunch of these systems that we know exist. But we don't know how this forms because conventional planet formation theories tell us that there should be an increase in mass of the formed planet as we go out in distance from the star. And this is obviously not following that trend. So what is happening here? So the idea was presented by Preacher and collaborators in 2024, where if you have big enough, these are two super Earth planets, if you have these two planets embedded in the disk, you create these dust traps that I told you about, and you start piling up dust there. But the interesting thing that they found when they compared the case for a single planet in red with the case for two planets in blue is that, of course, you get two rings in these two dust traps. This is dust surface density. This is only the dust, and this is the radial location. The planets are here located in the dashed lines. But what happens is that the ring you get when you only have one planet has more mass in it of dust than the one you get if you have two planets. So somehow by means of filtering in this, creating this dust trap, the outer planet is causing this sandwich ring to be depleted in solids. And that's really interesting because if you have less dust, you have less solids available for planet formation, and you have less massive bodies that you can form in that ring, right? In that location. So that could explain how we end up with systems like this, which is again important to sort of connect the protoplanetary disk phase to the planets and exoplanetary systems that we do see. So what was interesting for me in this study is that they did run the simulations for 3 different dust grain species, what we call the small, the medium, and the large grain dust grains. So the large, dust grains. I hope that's understood. So if you look here, this is the profile of the gas. Dashed lines are showing the case of only one planet, and black is for the gas, blue is for the small dust grains, green is for the middle dust grains, and red is for the large. And what I saw when reading this paper here is that there is a very different composition in terms of dust grain sizes of these 2 rings. And the profiles of these different dust species show up really different. So this necessarily will have to look different at different wavelengths. And that's exactly what I set up myself to do. To build the synthetic observations to see if I could say what is the observational signature of sandwich planet formation as it happens. And this is what was the result. So it is going to be published in a paper that I am finishing and hopefully will be submitting very soon. Again, I'm exploring wavelengths of instruments that we have available or are upcoming. This METIS instrument is an imager in the infrared that's going to come soon online in 2028 on the EELT, the Extremely Large Telescope, then ALMA, wavelengths, and sphere. And what we see here is that the profiles are very different for the different wavelengths, where we see a ring of dust here showing up in the sphere images, where we see very clear and distinctive two rings in the ALMA images. Again, we're tracing small grains all the way to the large grains in the disk. And it is a bit easier if we explore the radial profile of the images to see that the inner ring is a signature in all wavelengths. These are the radial profile of those images that I showed in different wavelengths. And we see a bump in most of the wavelengths. But when we go to explore the second ring, there is a clear signature that appears only in the large dust grains and not in here. So again, this means there is small grains in the sandwich ring that doesn't appear, that are not showing up in the outermost ring. And can we link this to observations now? Well, I think so, but it's not for sure, obviously. But this is a case of a very famous disk that's called HD 163296. And these are images taken with sphere and ALMA. Here we do have the spatial scale. So these are arc seconds. And then we are making sure that we have the same spatial scale. So with sphere, we only trace the inner disk where we don't have a ring outside. And that tells me that this is a really good candidate for my mechanism, well, not my, but the mechanism I'm studying, sandwich planet formation. Now, there could be that the first ring is puffed up and is shadowing the second ring, and that has been discussed in the literature. But there are studies that have looked into the composition of these rings and are estimating that the outermost ring is mainly composed of large dust grains, which nicely ties to my to my simulations, the simulations we did, synthetic observations for the sandwich planet formation case. So this is a wrap up, I think. What I mainly want to say is that what I'm aiming to build for this particular mechanism of planet formation, of sandwich planet formation, is where I compare the case of having two planets with one planet. How does it show when we have different values of alpha, of the viscosity, of the which related to the turbulence of the in the disk, when we have very low turbulent cases. We are investigating the effect of planet migration, dust evolution processes. We are investigating the effect of different observational techniques on trying to disentangle one case from another. This is all work in progress that we are having here, but I'd like to finish up with this, going a bit back to the start, which is this question of how do we link the amazing variety of substructures that we have in protoplanetary disks with the stars and the planetary systems and the planets that we find. It is necessarily through planet formation mechanisms. And in order to understand those, we need to use multi-wavelength observations and combine them all to puzzle and piece up all of these different pieces of information. So I leave you with a beautiful image of PDA 70, and I hope this hasn't been too much. Thank you so much. And that's it. That's it for me. I don't hear anything. Sorry, I don't.
Do you hear me now? Or we're muted?
Sorry, I didn't hear that.
Do you hear me now?
Yes, yeah.
Great. Do we have questions? So we have a question here from the Google Doc.
Okay.
What is the scientific definition of an exoplanet?
Wow. A planet that is outside of the solar system. It's around, yeah, I guess that's it. I don't know for sure. That should be my answer, but I imagine that's the definition. So.
Rogério has a question. He's going to come over.
Okay.
So hi, thanks for the very nice talk. So when you showed the integrated SED distribution of the star,
Yeah.
there is a drop.
This one?
This one, yes. Then you were saying that there is this drop like in the middle
Yeah.
here
Mhm.
where. Okay, so as far as I understood, this should be a gap in material inside.
Yeah.
But
Yeah.
we see such a drop when we look to SEDs of AGNs.
Okay.
And we always say that it is from silicates.
Uh-huh.
That would be dust grains. So could this be dust grains?
So
Special dust grains?
I actually have an extra slide that I can show if I go to the end of the talk of a real source that is actually showing, but it shows, at least in these sources, it shows us a peak emission at 10 microns. This is it. Sorry. So this is the SED for HD 163296, which is the target that I'm not claiming, but suggesting that would be interesting to a candidate for sandwich planet formation. And what you see here around 10 microns is the silicate emission, we call it like that. And that comes, I don't know if you're referring to these drops here. But
For us, it depends if we are looking to a Cipher-1 or a Cipher-2 galaxy. In one case, it's an emission, and the other case, it's an absorption. It depends how we are seeing the inner disk.
Yeah, in here, we only work with emission. So what I know about the silicate emission is that at 10 microns, it shows up in a lot of these disks, which is indeed a feature of the system having hot dust that's emitting at that particular temperature. So it is the silicate feature, we call it. So yeah,
it's a little bit different than the drop.
Yeah, I guess the dip is not. So when you work out the temperature that you should have your components at, I guess the dip is not very narrow. It's a dip. It is a lack of. You need an extra component to fit the baseline SED that you don't find, and that's when you know that there's material missing. Because as I've shown images from this particular source, we know that there are two rings in this. There are two gaps at least in this source. But we still get the silicate emission. So it's not about the small scale profile, but it's more the larger. So if you model this, this is the profile of the star, of the spectrum of the star. But if you try to model the components that at the temperature that you estimate, given the temperature of the star and the masses that we estimate of dust, then you sort of see that you're missing one of those bumps, and it's more on the baseline. The effect is more on the baseline rather than in the small scale features of the SED.
Thank you.
Yeah, you're welcome. Thanks for the question.
Do you have more questions? Students, or ask, can you come over?
Hi, you didn't mention which type of stars are central to these disks. Which type of stars do you find?
Oh, so we mainly study two types. So T Tauri, so these are less massive stars, and then we have Herbig AE stars. So those are more massive stars, but all of them are young. They are less than 10 million years. So these are stars that have been just formed. And of course, obviously, these are observations of the neighborhood for us, so to say. So
I wonder that the disks are of the size of the solar system disk, actually, 10 astronomical units. Why, actually, if the stars are so massive?
Yeah, so just to give you an idea, because that's your question that you asked, and I promised I was going to go back to it, but I didn't. So if, for example, if you look at this, so this disk that we simulated is 150 AU. So Neptune is at 30 AU, sort of, in the solar system. So that would be the position of my second planet. So we are working under the assumption that these planets are created outwards and then sort of migrate inwards afterwards. So these disks are truly enormous. And just to think that the solar system Neptune ends up here and we still have all of this to go. So yeah, I don't know if that answers your question a bit, but the observations that we have, so for example, in James Webb, when we try to observe disks with James Webb, because of the coronagraph, the mask that I told you we need to use, we essentially would be missing most of the solar system, all of the solar system in most of the disks that we're observing. So we're really limited by being able to peek into the inner regions, which you can only really do with the submillimetre wavelengths, because at those wavelengths, then the star doesn't emit, and then you have the chance to go into the system much more into the inner regions of the disk. So
more questions from the students? So I have one last question.
okay.
Thank you so much, Maria. It was very nice to hear all what's going on in this field. As you see, we're all extragalactic mostly in the audience, because we're talking about megaparsecs and parsecs.
Yes, yeah, no, we're small scale.
So it was very nice to see.
We're working on the tiny stuff.
To see the advancements, and there has been a lot, and I understand that there's a lot being built. So could you talk more about the prospects for the ELTs and GMTs, whatever?
Yeah,
what instruments
yeah, I'm really excited about that. I'm going to show you these images because they are relevant. So I'm excited about the EELT because the main problem we have now, for example, well, no, we have many problems, but one of them is the mass. What is the real mass of dust we have in these disks, right? At the minute, our estimates come only from the ALMA observations. But we know ALMA is only tracing large cold grains. So we're missing at least a bit of the mass. Like we think most of the mass is in large grains, but a bit of the mass is not being computed. And there seems to be, there's this problem as well in the literature that's been discussed, yes or no, we have a problem. It's called the mass budget problem, which is that, so from data on exoplanets and data on disks, there seems to be a lack of solids in disks to form all of the solid rocky material that we see in exoplanetary systems. So this is one issue. How much mass in the small grains we're missing? And we can't tell that with sphere, because sphere is only showing the surface. It doesn't tell us anything about the bulk of the small grains. It doesn't tell us density, mass, or anything. We can only do that with emission observations, right? And also optically thin emissions, which is another issue. So James Webb is good for that because it gives you measurement in the mid-infrared, but you can look into the small grain bulk of the dust. But unfortunately, because of these coronagraphic limitations, then it is limited to what we can tell. But METIS is a mid-infrared imager and also a spectrograph, I believe, that's coming on the EELT. It's planned to see light in 2028, and that would make a big change because it's going to give us really high resolution images of the small dust grain bulk component of the disk. And that's going to be really interesting because also these small grains are now thought to be the ones, because of these dust traps that we see tons of substructures. So it's clear that the dust is getting trapped by these different mechanisms. But the small grains are the ones that are able to flow, in a lot of the cases, to the inner regions through these gaps that are caused in the large dust grains. And these small grains are believed to be the ones carrying, in the form of ices, organic material. So if they're able to flow into the inner regions of the disk, then those are the grains that are going to deliver the material that's conducive to having complex organic molecules into the disk, into the inner regions, habitable regions of the disk. So that is why, I mean, METIS is really needed. I'm really excited for what's coming. And I'm actually, most of my time I'm spending trying to use the simulator because I want to make a lot of diagnostics for METIS. That's going to be my work in the immediate future. So I'm really excited about that. And yeah, that's in terms of exoplanets, but we have these missions that are amazing. getting more and more information about the planets and more spectra. And so it is very exciting. It is very exciting at the minute. It's really all coming together very nicely. I think it's exciting to be working in this field now.
Thank you so much. If we don't have more questions, let's thank Maria again.
Oh, thank you so much, everyone. Thank you for your time and your attention. Yeah, thanks for listening.
Now you're in YouTube forever.
Oh. I'm a star now.
Thank you, Maria.
Okay,
Bye-bye.
thank you. Thank you. Bye-bye. See you.
Agora a gente tem coffee break ali na salinha do lado.
Que isso?
E aí?
Eu não entendi se era para eu. Nossa,
Alguém? Assim embaixo.
Bye, Aninha.
Bye. It was very nice. I sent pictures to Hector and Tim, and they said hi.
Oh, thank you so much, Anna. This was lovely. Thank you. Thank you.
Bye-bye.
Bye-bye. See you.
See you.